Hello everyone, welcome back to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. In the last two videos, I spoke about me building a custom multimeter that does not exist on the market, so we cannot buy him even if we want to and if you have the money. That would measure four things at once and would basically calculate the efficiency of DC-DC converters. Personally, I need this because it would make my work easier, since I want to continue studying DC-DC converters and later other forms of switch mode power supplies. And instead of actually having four different multimeters on the bench with 8 cables or even more, this kind of device would definitely make my life easier. We've done pretty much everything we needed as far as the most difficult things, and today it's the last video of this small series of 3 videos in which I show you the final things to finally build this device, to assemble him, to write the program. I will put on the Patreon, on my Patreon page, I will put for all paying subscribers an archive with absolutely all the necessary files, including the software that I wrote and I have written on the Arduino Nano in order to have this project done. So there are only a few smaller details that need to be explained as far as the electronics goes. I will then explain what the software was all about. I will not go into such great details. I will simply assume that you know how to write source code in C or C++ or, well, any other language would be useful, even though we will be using C to program the Raspberry, the Arduino, not the Raspberry, the Arduino Nano. So I will not explain to you, every little bit of detail that goes into programming. I will only show you the overall process and what the program does so that you can understand what needs to be done, and I'm sure that you will be able to take some of these informations and apply them in other projects that you might have as well. So, and last but not least, I will show you a small demonstration that I've done earlier with a small DC-DC converter that I built a while back. I have performed some measurements and I will show you in very concrete terms, what are the results on the screen. Overall, like I said, this device turned out to be pretty nice. I am content with him. It's not super excellent, but it has decent accuracy, I would say, decent precision. So at least for some approximate efficiency calculations, this is pretty nice. Anyhow, before we move forward, first allow me to give you some good news and thank the sponsor of this video, which is PCBWay. They are currently offering you some discounts, because we are getting close to, Christmas time. If you need help creating your PCBs, maybe even assembling them with components, or perhaps you're building a device that needs a case and you would like that 3D printed or CNC machined, then you can definitely rely on the quality services of PCBWay. To make things even better, since we're moving towards Christmas time, they are currently offering Black Friday significant discounts for your offers, for your orders until the end of this month, followed by Christmas big sales discounts up until the end of this year. You might find that you can benefit from up to 50% discounts on ordered PCBs 3D printed objects, even CNC machined objects, free Christmas coupons based on your order's size, and they even have a lucky draw where you could win some goodies by just clicking these virtual boxes on the screen. Go check out what they have to offer, the links are in the description below. Thank you PCBWay for sponsoring this video, and now let's get started with what I want to show you regarding this particular project, so that later we can move on to an even more interesting project. So, just to recap shortly, we have discussed in the first video about a custom-made power supply, a rudimentary one, but still good enough one that allows us to use basically a recycled 3.7 volt lithium accumulator that we can recover from an old phone. To give you a good example, this is what I'm talking about on the bottom. So this is my final 3D printed case that I made for myself. On the very bottom of this case, I have placed an old accumulator from a very old phone that I had lying around, but it's a pretty high capacity accumulator, a 3.3 or 3.5, I don't remember exactly, but around 3.5 amp hours, which was pretty big back some 15 years ago or so when I bought that particular phone. This accumulator is still working, not at full capacity, but it's still working. There's no point in throwing him out on the garbage, to the trash. So I have used this here, of course, a connector to recharge him with an external charger, an on-off switch, and these three boards, handmade boards, are basically low battery indicator, an under voltage protection, and a DC-DC step-up converter, so that in the end we can have 5 volts to power our Arduino. Okay, in the second video we have discussed about signal conditioning. In order to take 4 measurements, completely different kind of measurements, 2 voltages, 2 currents, we need to, of course, convert all of these voltages, all of these things, actually, 2 voltages, 2 currents, into voltages that are acceptable by the Arduino board. And this is what we discussed in the previous video, number 2 of this series. Now let's discuss basically what is left, which is the connection between this Arduino Nano and the Nokia 5110 LCD screen, and like I said, the software. Now I chose Nokia 5110 LCD screen because of 2 reasons. First, because, well, such screens are available on the market. I can buy them in relatively large quantity, meaning 10 or more pieces. They are relatively cheap. They're not super cheap, but they're not expensive either. And on top of that, they are able, like we see here in this picture, these screens basically have a matrix of pixels. Unlike other screens where we can display just characters, we can display pretty much anything on these Nokia screens, even drawings if we really want to, and we can have up to 5 different lines of text of standard height, let's call it like that, standard size, or we can of course combine 5 lines with bigger size, bigger fonts, and have something in between. As we can see here, I have 3 lines of standard size text and 1 line of double size text that is being displayed at the same time on the screen, which is not possible to be done with other screens, with other LCD monochrome screens. unless they are very big, and we would probably need to do some research as to what it takes to program those screens. For these Nokia 5110 screens, we can find the source code already online. We can find the libraries. It's really easy to work with this screen. So these were the reasons why I chose this kind of Nokia 5110 screen. Now, from an electronic point of view, I don't think there can be anything more simple than that. We have, so the Nokia 5110 screen has 8 pins in total. Out of these 8 pins, 1 pin is the ground, pretty logical. 1 pin is the VCC, the power supply, again, pretty logical. 1 pin is the backlight, which I did not use due to power consumption reasons. And because I will never use this device in a dark environment, I will always have room lighting, so backlight for this screen doesn't make sense. So I have not connected this pin. Be careful that this VCC pin needs 3.3 volts, not 5 volts. So you would connect this to the 3.3 output pin of the Arduino. And on top of these 3, we also have 5 more pins that are related to the CPI communication protocol. And essentially, you connect these pins through some resistors. I chose 10K resistors, but the value is not critical. You could choose slightly lower or higher value resistors. Through these resistors, you need to connect these 5 pins to 5 digital output pins on your Arduino Nano. It doesn't matter which ones, it matters just that they are output digital pins for the Arduino that you use. In software, we are free to basically choose whichever pins we use. Because they're not, the software library allows us to just redefine these pins however we want, and I will show you in a moment. And that's pretty much it when it comes to, you know, connecting the Arduino to the screen. Of course, you need to have the plus 5 volt and the ground connected to the power supply that I mentioned earlier, like here. The output 5 volts. This is why we have this linear regulator to have a very nice smooth 5 volt power supply for our Arduino. It is important because the higher quality power we have for the Arduino, the higher precision we will obtain, because the ADC inside the Arduino takes the 5 volt by default, takes the 5 volt power supply voltage as a reference for the absolute maximum value that he can convert into, you know, digital numbers. So if you have a low quality 5 volt voltage that comes from something else, like, I don't know, a very poor DC-DC converter or something like that, then of course you will have some jitter in the readings that you will get on the ADC. And something that I haven't drawn here because it didn't make sense, but all of these analogic input pins for the Arduino Nano, all 8 of them, need to be connected to these output pins on the signal conditioning board. Okay, this is why I have labeled these out ADC 0, 1, 2, 3, 4, 5, 6, and 7. Okay, these are exactly the pins that need to be connected here or the Arduino Nano. And since we are using 8 of them, you must use Arduino Nano. You cannot use an Arduino Uno because you don't have 8 ADC input pins. Anyhow, and basically this is it when it comes to the electronic part. All you have to do is basically build all of these boards, assemble them, and write the software on the Arduino. Okay, Let me quickly show you the construction process, at least what I've done. Of course, in your case, you might have it differently. So, like I said, I have created a big enough box, plastic box, 3D printed one for everything. On the absolute bottom, I have put everything that was related to the power supply. So basically we have here the DC-DC converter, we have here the low battery protection circuit, the low battery indicator, and the accumulator himself. On top of this, I have come with a plastic, a piece of plastic, okay, like we see here. And on this piece of plastic, I have assembled, I have fixed the signal conditioning board, which is here on the lower side, and the Nokia screen with the Arduino. Like we see here, I have soldered these resistors directly. And this is also why I chose these particular pins to be used for the Nokia screen and not different ones, because they are exactly in parallel to each other, and it makes things much easier to do. Okay, and that's pretty much it. And of course, on top of it all, I come with yet another piece of plastic which acts like the cover. And on the outside, I have these electric connectors. I don't know how to call them in English. I don't know the English word, but they are typical to electric installations, electric wiring. Okay. This makes it easier because, you know, we need to have 8 different connectors. This device needs to have 8 different connectors because he needs to connect to 8 different things. Even though the ground is common, we still need to be able to have 8 different connectors in total. It made sense, and it was a lot easier for me to just use these kinds of connectors, electric connectors, and just screw whatever wire I want on the outside whenever I need them. Okay? And this is the finished product, seen photographed from the top. And it works pretty nicely for me. Also, the screen is clear enough. It displays maximum amount of information that we can possibly want. So on the first line of text, we see E in front. This is from input. So on the first line, we see the input voltage and the input current. Basically, let me refer to you to this schema. This is the input voltage and the input current, so between the power source and the DC-DC converter. Okay. On the second line, we see O from output. Again, a voltage and a current. This is the output voltage and output current from the DC-DC converter that will then go to an artificial load. Both the power source, just to remind you, both the power source and the artificial load must be external devices. Okay, this multimeter has no means of providing power or drawing current from the DC-DC converter. But that's not the problem, since in our lab we have such a thing anyway, right? On the third line, we have R from a ripple. In software, I am attempting to measure the ripple voltage for both input and output, even though, technically speaking, we only care about the output ripple. Now, take this with a grain of salt, as you guys say in English. It's technically speaking, in order to accurately measure the ripple voltage, I would need to have means of sampling the input and output voltages several 100,000 times per second, because of course a DC-DC converter works with anywhere between a few tens of kilohertz up to maybe even 1 megahertz. So needless to say, in order to accurately measure the ripple, we will need to use an oscilloscope. Really, we couldn't get over that. But in order to have some sense of how big the ripple is, we could perform some calculations in the software. The Arduino is able to have a few thousand samples per second for his ADC, so we can detect to a certain degree how big the ripple is. And I'm choosing to have this kind of information, displayed on the screen, at least just for fun, just for having an approximate value. And then, of course, with twice the size text, we are displaying the percentage, the efficiency of whatever board we are testing. So, as you can see, all of these informations come displayed nicely on the screen. And this is what we have in the end. So, in terms of physicality, this is pretty much it. There's not much more that I can explain to you. Now, let me explain a little bit about the software that I had to write for this device. It's not big, it's pretty clear, pretty simple, but it's worth going through him to be able to understand better what I've done here. So I am using a few libraries. cpi.hash, this is a standard library to communicate with other modules via CPI protocol. You don't need to, as far as I know, you don't need to do anything to use this library. However, I have also used a couple of Adafruit libraries, Adafruit GFX and Adafruit PCD 8544. This 8544 is the code for the for the controller of the LCD screen that's used in Nokia 5110. These libraries needed to be installed, so if we go to Tools, Manage Libraries, and I'll ask you to have a little patience now because it's loading quite a lot of libraries that I have installed. I will show you which ones they are. So you come here to Library Manager, you wait for him to do his business, to check if there are updates available and all sorts of other things. And then you write Adafruit GFX in this search box, and after a while he will search. And let's see what we have. Yes, here we have in this list Adafruit GFX library. I have 1.11.9 version installed, which happens to be the last version right now. Of course, if you look at this in the future, you might find that there are newer versions of this library. If you don't have this installed, then you will have a button here to actually install that particular library. You use that button, and of course we need to search for this PCD 8544 library, which again you will find pretty easily. Adafruit PCD 8544 Nokia 5110 LCD library. Again, mine is installed. I have 2.0.1 version. There is one newer version, 2.0.3. However, for whatever weird reasons, I was not able to install this. I'm still very stubborn in using Windows 7, which is very old. Arduino 1.8.13, which is again pretty old, but newer ones don't run on Windows 7 anymore. Anyway, due to these reasons, sometimes I need to settle with lower versions of libraries, software libraries and whatnot. Anyway, it doesn't matter. You install whichever version is good for you. Click install and you will have that library installed. Anyway, let's move on. I have a bunch of definitions here that you will have to change if you decide to build this project and to build this project by downloading my files and using my software. First definition, LCD contrast, number 35. This is just a number that I saw was good enough for me. This is a number that, like it says, defines the contrast of the LCD screen. If you choose a too high contrast, you will basically not see the text very well on the screen. Even here, if you take a look, you will see that the background is a little bit gray. So I mean, for me it's okay. This is a bit exaggerated on the picture. In reality, it's not quite so much gray. But anyway, the higher value you put for this LCD contrast, the more the background will be blacker and will not allow you to see the text very well. You know, the lower this contrast is, the better you will see the text. But I'm guessing at some point the text will be too faded himself. So anyway, play with this number as you see fit, LCD contrast. Another definition that's needed for further calculations is power source voltage in millivolts. This is the voltage that you send to the Arduino to power him. It's the voltage that it's being output here on this entire, you know, power source. It's the voltage that's given, it's being given by this 78L05 voltage regulator. No two voltage regulators are perfectly identical, and because this voltage matters, you need to basically, in the end, when you have finished creating your boards, you have assembled them, and you need to deal with the software, you need to take a multimeter, preferably as precise as possible, measure that 5-volt voltage and write that here in millivolts. In my case, I had 5.044 volts, so 5044 millivolts, right? So I have written this here. You will have to change this for basically yourself. And we have a few more attenuation or amplification factors that are calculated in these particular formulas. These resistors are all part of the signal conditioning board. Okay, so before you place these resistors on the board, you are recommended to measure their resistance and then calculate these values. Root 33 plus root 30, everything divided by root 33 is for attenuation factor voltage input, root 32, root 34, and so on and so forth. Like I said, you will find them here. Okay, root 25 is here, root 23 is here, root 26, 24 is here, 30, 33, 32 and 34 are here. So you need these because of course, since these op-amps are amplifying these signals, and these other op-amps have these attenuators placed in front of them, each deviation from the nominal value of each resistor will cause a different amplification or attenuation factor. And yeah, you will in the end you will obtain slightly incorrect values. So in order to compensate for that, you know, we need to know exactly what attenuation or amplification factor we have, and this is how we do it. We calculate these values and we put them here as constant. And that's pretty much it as far as what you need to measure, calculate, and change for yourself is concerned. Then we have an initiation of the display with the Adafruit library, and we are calling this function with 5 parameters. The pins that we have used for connecting the Nokia LCD screen in this particular order. So in my case, it's 3, 4, 5, 3, 4, 5, 6, 7, because these are the pins. Okay, D3, D4, D5, D6, D7. So the order is from right to left of these 5 pins: clock, data in, data out, chip enable, and reset for the 5110. If you decide to use different Arduino pins, then you will have to, you know, change these numbers. So these numbers are the digital pins of the Arduino himself. Okay. Then we have a bunch of variables that I use to store data that comes from analogic digital converters, also some counts, some minimum maximum variables, and a variable for time, because I am constantly reading values, but every once in a while I have to stop, perform the calculations, and reset, and then move on to, you know, the next set of values that need to be calculated. I have a function that I will jump over here. You don't have it in your source code. I needed this just because I had some non-linearities for the second channel, for the output current measurement. If I had very low current values, like under half an amp, I had some non-linearities that were causing a bit of too big errors, and in order to correct them, I've done some voodoo stuff here. So I'm just gonna jump over this. I'm going to assume that it was something weird happened only for the second channel for the output current, you know, because the first channel, the first circuit did not needed any correction factors to be applied. Anyway, I'll just skip over. Then we have the setup function of the Arduino, typical setup function. We need to write these for the LCD screen, and this is where we specify the contrast. And we need to set the time to basically be, the time variable needs to hold the moment in time when we are starting to do this, because from that moment, every 200 milliseconds, we need to stop, calculate, display, and then continue. Okay, and in the loop, this is exactly what we are doing. We are reading the values from A0 to A7. These are the input ADC pins. Okay, we are reading them all one by one en masse. We are calculating the square of those values, and we are storing that particular square in a variable, and we are also counting how many reads we have done, and we are storing that in a different variable. Also, we are initializing some we are setting the minimum and the maximum for that particular ADC channel, because we will, in order to determine the ripple voltage, we will need to know what has been the maximum value that we read and what has been the minimum value that we read. Otherwise, we won't be able to tell based on this squaring and the other calculations that we will do. The reason why we don't store values as they are, but we rather square them, is because I want to create, I want to store the root mean square value of everything. This is what, because if either voltages or currents are varying in time, I don't care about their variation. I don't care about, first and foremost, I care about their root mean square value. Okay, so in order to calculate root mean square, I need to square all the individual reads and to count those reads and then to perform some calculations with them. Okay, so this is why I'm squaring these. Now I'm doing this over and over and over again until I hit 200 milliseconds from the last time that I performed some calculations. And this is why we have this if here. And if we have hit 200 milliseconds or more since the last time we calculated and displayed things, then we are going into the actual calculations and display on the screen. If not, we are just keeping on reading new values from the ADC. So if we need to calculate and display things, then first we need to convert these values into actual voltages, raw voltages that the ADC has read on each input. And this is why we divide these squared values, these values that were squared earlier, we divide them by the total number of values that were calculated. We are performing the square root of that division, okay? And this gives us the RMS value in terms of digital value. We multiplied this by the reference voltage of the ADC, which is the power source voltage of the Arduino himself. This is why we needed to measure the power source voltage, and this is why it's not good to just consider this 5 volts precisely, because it rarely is 5 volts precisely. And of course, since this is in millivolts, we need to divide this by 1000 to get these 2 volts. And then with this, we divide this to the number of values that we have maximum. And that's 1024 because Arduino Nano uses 10-bit ADCs. 2 to the power of 10 is 1024. And this is how right now we have for every ADC channel the value in volts, in actual volts, okay? Then we go on to define some more variables because we need them here, and we go to calculating real voltages and real currents based on these ADC voltages. Because like I showed you in the signal conditioning schema, we are using 2 ADC inputs for everything that we want to read, because we for smaller values we want to have some more precision. For higher values we can let go of that precision. So for instance, for the input voltage, we have ADC4 and ADC5 channels, but they are having different readings. So we need to see if the reading on the 4th channel is within 0 to 5 volts. If that is so, then we can use that reading. If that reading has reached around 5 volts, we will simply assume that the voltage is actually higher, and so we need to read ADC5 input that has been attenuated. And of course we need to calculate to take this attenuation into calculation, and we need to do this for both voltages, and this is what we see here. If the value on channel 4 is less than 4.9, then we are using this value as she is, and we are calculating the ripple as the maximum point, the maximum voltage for that, the maximum point for that channel minus the minimum point multiplied by power source voltage divided by 1024. Anyhow, if that value is above 4.9, then we need to take into account the 5th channel and multiply it by the attenuation factor, and that's going to be the voltage that we will have there, okay? And same with the ripple. We have to calculate ripple based on the 5th channel minimum and maximum values, okay? And in a similar way we are doing with currents as well, except a bit in reverse. Currents are being the voltage for currents is small by default, so we are amplifying that voltage with some non-inverting amplifiers in order to have a higher voltage for lower currents. Okay, so if the value is on those channels is smaller than 4.9 volts, then we are taking those channels into consideration, and we multiply them by a certain factor. If the value on those channels is bigger, then we are simply taking the corresponding other channel, and that other channel is directly as he is. Now, since we have half a volt per amp coming out of INA 180 measurement amplifier, we need to, you know, multiply that number by 2 in order to get 1 volt per amp, in order to know exactly what that current was. Okay, and that's pretty much it. And then we get to calculate. So when we have both voltages calculated and both currents calculated, we can calculate the efficiency, which is basically voltage output multiplied by current output, everything divided by the product between input voltage and current. Again, so it's power output versus power input, multiplied, of course, by 100 in order to express that in percentages. And that's what we are displaying on the screen. Or if the input power and current product is 0 or less than 0, well, they will never be less than 0, but if they are 0, then of course we cannot calculate this particular division. So we are simply displaying 2 question marks. And that's pretty much it. And then we call some functions that are related to the Adafruit display library to, you know, clear the display, set text color, set text size, and basically start to actually display on the screen all these informations that we have calculated earlier. Okay, for the input we have letter E, then the voltage, then symbol V, and then the current. If the current is below 1 amp, I'm choosing to display that as milliamps, so that I have higher, a bit higher precision in terms of the display. If the current is above 1 amp, then we are displaying that current in amps. With 2 decimals, so we are losing a little bit of precision, but anyway, this way we are able to display up to 10 amps of theoretical maximum current. Okay, I'm also changing from point to comma because, you know, here in Europe, in most of the Europe, we use comma as a decimal separator. So it's not, I don't know, 3.4, it's 3,4. This is just a personal preference. And then I display everything. I print these informations for the input. I do the exact same for the output, just different voltages, different values. I do something similar for the ripple. And then the efficiency as well. I just set text size to 2 to make the text bigger. Okay, and then before I finish everything, I reset all of these values so that I start all over again with a new cycle of reading ADC values, calculating everything, you know, and displaying them more. So yeah, so this is pretty much it. The whole software is 189 lines. It's a small software, but it's good enough. It does what he does what he needs to do, and that's pretty much it. And this is how we can have a nice tool, right, to ease our work when it comes to dealing with DC-DC converters. Again, I remind you, only DC-DC converters with common ground. You cannot test isolation power supplies. You cannot test inverting DC-DC converters. For those, we will need a different device, or just go back to 4 different multimeters and measure separate things. Anyhow, I'm showing you here a test that I have done with a DC-DC converter that I built a while ago. You see him on the bottom of the screen, close to the edge of the screen. So, to explain a little bit what we see here, like I said, my device has 8 different connectors. I have chosen to separate them 4 by 4. The 4 on the left are for input, the 4 on the right are for output. The top left 2 connectors are for the input power supply. So you need to come with, you need to connect here a power supply, a lab power supply, or really any power supply that you have. This is why you see 2 wires going to the right of the screen into my power supply that it's not visible on the screen. On the top right side, there are 2 wires that are going into an artificial load. Again, it's also on the outside of the screen because I didn't have enough space to film that and have that everything in the screen. You need to connect there any form of artificial load, even just a simple resistor, because there's nothing to draw current from your DC-DC converters. So if you do not draw current, you will not be able to measure efficiency. Pretty logical, I would say. And on the bottom connectors, left and right, you need to connect the DC-DC converter. The input of the converter needs to be connected on the left, the output on the right. Okay, and we have a few wires that go into this box, into this device, and the device does what he needs to do in order to tell you that right now you have 75% efficiency. So let me give you a slightly better zoomed in image. I know the quality is not so good. My camera sadly is not all that good. So let me explain to you what I have done here. So let me zoom in. Okay, I have 12 volts on the input, 5 volts on the output, because I have set my DC-DC converter to output 5 volts, and this is what we see with the E and O lines. I am starting to draw current right now, about 800 milliamps, 900, 1 amp. Okay, you can see that on the output line, and on the input line, of course, you see a different current, and 74-75% efficiency overall. At some point, if I go above 1.6, 1.7 amps, my DC-DC converter starts to fail, so you get to see something like 60-ish% efficiency. Anyhow, and this is pretty much how everything works. So for me, it's a pretty nice device. It's of great use, and I hope this will be useful to you as well. So thanks a lot for watching this video. Soon I will come with a new project. I'm already designing him, an even more, I would say, at least for me, an even more useful project, the device that will calculate the it will discharge an accumulator and will calculate the total capacity in watts-hour of that accumulator. This is so that we can test cheap accumulators on the market if they are what they say they are, or you know, if we basically get impaled by those people selling cheap Chinese stuff. Anyway, that's gonna come soon. This month, I mean, well, in December, next month. So stay tuned. Thanks a lot for those who support this channel on Patreon. Link is in the description. Thanks for watching this video. I hope you found him useful, and stick around for more interesting things to help us prepare for the future that we're heading to. See you later.